Um, Something I wanted to ask you all what you think about. We had talked about next week, instead of coming here, coming to the shop, and we were going to assemble an engine. I hadn't really thought that fully through. A week from tonight is the EWC board meeting. And as some of you might know, I'm running for one of those seats. So if I get elected, I kind of need to be at that board meeting. Well, thank you very much. I appreciate that. So, if it's okay with you guys, what I was going to suggest, let's see how the election turns out. If I get elected, I really need to go to that board meeting, though. And would would y'all be available if we just moved it one night from Tuesday night to Wednesday night? You have to work. Um, what's that? Yeah, that'll work good. You get off work when? Oh, you work pretty late then. Um, Thursday night, what do y'all have going on? You work that night too. Well, I hate to say it, probably any night we pick is going to interfere with somebody, isn't it? Anybody got a better idea? Um, I suppose I could do that. That work for y'all? Okay, we'll do that then. And maybe we just plan for that, and then it don't matter. You don't got to keep track of how the election goes. What if we just plan Monday night um, at 6 o'clock at Buckaroo? Um, and if you would come in the doors that are at the southeast corner of the building, and we'll put an engine together, all of us together, if that sounds all right. Cool. Well, thanks for helping me make a plan there. Um, so last week we talked about turbos, and there were some questions about the variable geometry turbos. And so I tore one apart today at the shop and brought it in with me. If y'all want to, come gather around and we'll look at some of these small parts that are going to be hard to see from your seats. So these pieces I've got split normally are together like that. So what we're really wanting to do is this is our fresh air intake. So our air comes into this from our air filter. And it will be compressed by this wheel and pushed out here. That's what we're wanting to do. Is we're wanting to suck in atmospheric air here and have it come out here as compressed air. So we're blowing that into our engine. But the way we get that is by turning the shaft fast and turning that compressor wheel, it's called, fast enough to blow hard, right? So that shaft is being turned by this fan blade. And the way we direct our exhaust at this fan blade and how much we put to it is going to determine how fast we spin this, how fast we spin the shaft, how hard we can blow there, right? So this is the variable geometry. What Joe's doing is just exactly what would happen. There's actually a little actuator in here that turns this lever. And this lever, here, Joe, try something. Put the end of your pin in that hole. That's what this lever does. So I'm going to go ahead and lift that plate just so you can even see those passages a little more clearly. So the exhaust that we're using to drive this whole thing is coming in here, and it's swirling around, and it's coming between these pieces. These pieces are directing the flow of our exhaust. And different companies call them different names, but they're exhaust directors. So if we have them wide apart like this, there's a big opening there, and the exhaust can flow through there, and we can get the same volume of exhaust, the same cubic feet of air through there, with it flowing at a much slower speed. And you can also see it's pointed more towards the center of the wheel. So we're going to be pointing it kind of about the direction my finger's pointed now. But if we take these and we pinch them over like that, we're pinching that space between them down. So to push the same volume of exhaust through that small space, it's got to go much faster. And you see the direction where instead of pointing it like my finger is now, we're pointing it like this, right at the tip of these blades, which I'm actually backwards because it's upside down. We're pointing it this way. That's right. Good observation, Joe. This upside down coming over here. I got myself turned around backwards. Good eye there, Joe. So instead of pointed like this, we're pointing it more like that, right at the tips of these where they got more leverage. So we increase the speed of this as well as the force we're putting against it. So does that make sense? How you doing, Donna? What's that? Sure. No, actually, what we had just discussed, if it's okay with you, next week, instead of coming here, we're all going to go to the shop at Buckaroo and assemble an engine. So tonight will actually be our last night in this building, if that's okay. We appreciate you asking, and thank you very much. So what this plate does, of course, is just control all of these at once. So we can pitch them like this, where we've got big spaces and the exhaust can flow slow, or we can pitch them all like that, where we got small spaces and it really blows at a high speed. You're just pretty darn sharp, Joe. That's awesome. So some of these, now this particular one doesn't, because the way that they've designed the ends in these slots, but a lot of these are made where you can go all the way shut with them, like you talked about. Well, if they're all the way touching each other, where can the exhaust easily flow through? Nowhere. It was a trick question. I'm sorry. It kind of plugs it. So, for example, the last about 10 years of production of Dodge pickups have used that as an exhaust brake. And when you have the exhaust brake mode activated, all they're doing is pitching these all the way shut against each other and, in effect, plugging the exhaust. So, um, so there's no true Jake brakes in pickups, but in pickups there are exhaust brakes which basically do this. They just plug the flow of exhaust, or as much as possible. They can't completely plug it, and that bogs the engine down. Now, a true Jake brake, what it actually does, I guess we don't have. Well, the engine in the hall. We all want to go out there real quick for just a minute. So, for those of you who may not be familiar with the term, Jake brake is a term that when you've heard semi trucks coming down a big hill and they make this noise, what they're doing is turning on a device called a Jake brake, which slows the truck down without using the actual brakes on the axle. And it's a device on the engine. And what it does, let's get this turned around to about where we want it. So this is actually intake valve, and we don't have as good a view of the exhaust, but you can imagine. So the piston, well, we've talked a little bit about how we got 4 strokes, and 3 of those take work to accomplish, and the 4th one is our power. Well, what the Jake brake actually is, it'll be a big device that's here above our rocker arms typically. And so right after the compression stroke has come up, like, I think we're in the right spot. Right there, after we've done all the work to compress all that, there's a plunger right here on top of this that pushes down and opens our exhaust valves. So we've done all the work to compress that, and then we're just going to let it out and not actually use any work from it. Now, in a lot of the older engines, they were not disabling the injector. So the injector was still firing. And of course, as you can see, there's so little space there, you couldn't open that valve until it had come down just a little bit, the piston had. So you were actually starting the whole combustion, and then right after it had just started, you're opening exhaust valves, and it blows. I mean, you got that, the bang, instead of shoving the piston down, the bang was making a loud noise going out in the exhaust manifold. On a lot of the newer computer-controlled injection systems, they're able to not fire the injector when those are on. So that's why a lot of the newer trucks, the Jake brakes are not nearly as loud as they used to be. But that's what the Jake actually does. And in a lot of the semi-truck engines, and there again, the vast majority of semi-truck engines will be inline 6-cylinders, similar to this. They'll actually have that available as stage 1, 2, and 3 in the Jake brake. Stage 1 will do that with 2 cylinders. Stage 2 will do it with 4 cylinders. And stage 3 does it with all 6 cylinders. So we're doing all the work for the intake, well, for the exhaust, I guess, yeah. We're pushing the piston up for exhaust. We're pulling it down for intake. We're pushing it up for compression, and we're using energy that we've transmitted through the transmission and hooked to our axles. We're using energy to do all those, and then instead of creating any power, we're venting it on what would normally be our power stroke out the exhaust valve. They're just got a big plunger right there on top of that tip of the exhaust rocker arm. So that's a true Jake brake. And there is a company making those for pickups. They're incredibly expensive, and I've only ever seen one. But it's pretty common to have an exhaust brake, which is typically just a flapper door that closes in the exhaust pipe and kind of plugs things up where they can't flow good. And they're pretty effective, but they're probably only half as effective as a true Jake brake is. No, sir. Nope, a true Jake brake has nothing to do with the turbo, other than they shoot fire through it. So, any other questions about these variable geometry turbos? I guess just one more comment I wanted to make is you can see with all these moving parts in the flow of exhaust where we have all the black soot, how that, and this one is a used one, but I cleaned it pretty well before I brought it in. You can see how when all these moving parts get jammed up with all the black soot from the exhaust, why eventually it gets clogged up where it won't work. And this little lever right here can't move this like it's supposed to, and it'll get jammed in one position. And at that point, in a lot of cases, we'll disassemble the turbo and try and clean it. But what we wind up finding a lot of times is that by that point, these little tabs and these slots, they're badly worn out, and in many times this actuator slot here is all wallered out, and the turbo's just shot, and so you shell out $2,500 for a new turbo. Actually, what it does is when you're calling for more power, it pitches it where those openings are smaller, and it increases the speed of the air blowing, and like we said, the angle. So I know it sounds backwards until you really think through the whole flow of events, but actually when you're calling for more power is when it will pitch them over here with the space relatively small. And when you're calling for less power is when it'll open them up and have big spaces where the exhaust flow is low speed because you got lots of room for it. So the other thing that kind of wanted to talk about tonight was some of the thought process that goes along with diagnosing problems. And having an understanding about how all these parts of the engine are supposed to work goes a long ways towards figuring out what might be the problem when one's not running like you want it to. But I wanted to talk about a few different things a little more in depth as far as diagnosing problems. When I first started, why we didn't use the word diagnose, it was troubleshooting. But as time goes on, why we gotta all use bigger, fancier words, right, for the same thing. So, for example, when we have somebody tell us that their vehicle won't start, well, the first thing we'll ask is, does the engine crank over and not fire, or does it not crank? Because if it cranks over and doesn't fire, you're actually looking at a problem with the engine. But something we haven't really talked about a lot, but a lot of you are, I'm sure, aware of, is to start the whole process we've talked about with the 4 strokes, we've got to start that engine spinning over so that we can suck the air in, and typically what we've got going on is an electric motor that will temporarily engage to the connect to the crankshaft through the flywheel and some gears and get that spinning. And your average electric starter motor is going to spin that crankshaft at about 150 RPMs. Well, you've probably noticed if you've looked at your tachometers and things that your engine will kind of sputter and cough and try and die if your idle speed comes down below about 600 or 700 RPM. So, that starter motor's just getting it spinning enough that it can kind of get going a little bit, but as soon as it actually starts firing, it's got to bring that RPM up quite a bit. It's interesting, there's several modern engines that the difference in how well they'll start is dramatically different between 150 RPMs and 125 RPMs. 3 engines I can think of off the top of my head, you'll crank and wonder if they're ever going to start, and they might eventually cough and sputter and try and start at 125 RPM. And if you can spin them 150 RPMs, they'll fire right up. And you really can't tell that difference by ear real easily if that's not an engine you use every day, and you can kind of notice it's cranking a little slow. But I wanted to talk real quick about the whole starter motor system that cranks our engines up to get them going. So typically we're going to have a battery or multiple batteries. It's going to be our power source. And it's a DC system, so it's got to make a complete loop to do anything. So we'll have cabling from this negative side of the battery that's typically, this is a symbol we're going to use for connected to the chassis. And so what we may be doing with this is bolting it to the engine block. And this side of our system is going to go through several switches, but when we complete the other side of it, it's going to likewise connect to the engine block. And so actually we're using the engine block as part of our circuit, but our circuit has to make a complete loop in any DC system to do anything. So anyways, this is typically going to go to our ignition switch. So the switch that we put our key in and turn is ignition switch. That's a point where we can open and close this circuit as needed. Then typically we're going to have some type of a safety switch. If it is an automatic transmission vehicle, this will be built into the shifter so that it forces you to have it in park or in neutral for it to close this switch. If it's a vehicle with a manual transmission, this is typically on the clutch pedal. Won't complete the circuit if you don't have the clutch pedal depressed. But in one way or the other, we'll have some kind of a safety switch that interrupts it. Then typically it will go through basically a heavy-duty relay, but in this country we tend to call it a starter solenoid, but it's basically a set of contacts that complete the circuit from a low voltage side to a high voltage side. But anyways, it's just another, in the general description we're looking at, it's just another switching point. And I'm going to put solenoid. And then that will get to our electric motor. That, like I said, it's got some gears that snap in and out to connect it to our crankshaft to spin that crankshaft. And then there again, the most common thing we see is the starter motors typically spin our engines at around 150 revolutions per minute. So if you're hitting the key and nothing's spinning, this is kind of what you want to look at for possible problems. If we don't have enough voltage in our battery, this electric motor doesn't have enough energy potential to turn all the metal parts and, working the compression stroke of all our cylinders. If we've got corrosion at these connections here, that's another possible thing. If there's battery acid that's gone down inside the sheathing and corroded the copper strands inside these cables, that's another possible thing. We actually run into that fairly frequently. And what we'll do is take what we call a DVOM, digital volt ohm meter, and just check the resistance from this end of the cable to that end of the cable. And if you've got more than about 5 ohms, it's going to be a problem. So you can actually have a problem at the ignition switch. And most modern vehicles incorporated into this ignition switch point is going to be some theft prevention stuff. Most of your keys that require programming, that programming is actually programming a transmitter in your key that communicates with a radio receiver or a Bluetooth receiver in the vehicle that makes sure that, hey, we're not jamming lock picks and some thieves' tools in there. We actually have the key, and this is the key that belongs. So we're seeing more and more troubles with that all the time, where the transmitters in the key are a problem and not actually completing the circuit at this point, not because the key's not turning the physical part, but because the transmitter in the key isn't communicating properly with the anti-theft receiver. Safety switches do malfunction, but they're not something we see a lot of problems with. But they do malfunction. Either the switch that's on the clutch pedal or the neutral safety switch that's typically mounted right on the automatic transmissions. Solenoids are a fairly frequent failure, and the electric motors, as you can imagine, they're in a harsh environment, and we work the daylights out of them for a few seconds, and then we haul them around and bang them and splash mud on them, and then we work the tar out of them for a few seconds again later. So they take quite a beating. Something that we run into a lot that I might talk about a little bit on this solenoid. I'm going to draw it in mega scale here. As in, I don't know, 20 times larger than it actually is. But what we have in a typical starter solenoid, I'm going to label this one high amperage input, and this one our high amperage output. So to get this one's, for example, going to be connected by a big cable to our battery. I'm going to label that B+. And this one's going to be connected by a large connector or large conductor to our main motor, starter motor. And in here, we're going to have a little electromagnet. And the little wires coming off of it, this is going to be a ground, and this is going to be coming from our ignition switch, either directly or indirectly. And so what happens when we power up in a winding like that in an electromagnet? It becomes magnetic and pulls ferrous metals towards it, right? So what we typically have is a ferrous metal disc here that's made to suck into that electromagnet when we energize it. And then attached to it, we'll have a copper bar. So you can see that when we energize this electromagnet, it sucks this whole thing down, and it brings that big heavy copper bar where it contacts all across here. So our amperage flow is from this contact across that copper bar and through here. And this is the way anything that's typically referred to as a relay, or most things that are referred to as electric solenoids, are made to work. We can take little bitty wires and we can control this, but what we're controlling is high amperage flow devices that require a lot of electricity. But imagine how big our ignition switch on our steering column would have to be if we were actually switching all of that high amperage. We'd have to run the battery cables that are this fat clear up through our steering column, and well, it's a whole lot nicer to be able to run little bitty wires up through there. So what happens whenever we break this is we have a spring that pushes that contact away. Well, as that contact is coming away, I'm going to draw it part way up, and we're breaking that circuit. If you've ever hooked up, for example, jumper cables, what happens right as you disconnect them, or in some cases right as you connect them? Spark. You get a big bright flash of spark there, right? As the electricity's trying to still flow, but we're breaking the circuit. Well, you'll have that here too. You'll have a spark right here, and you'll have a spark right here, and it'll make a little bitty burn spot right there, and it'll make a little bitty burn spot in a pit right there. And of course, it'll do it somewhere on this side. It may be there on this particular time we open those contacts, because that may be what happens to be the closest spot. Now, next time it might be a spot over here. Well, you can imagine, okay, we do that 500 times. We've got 500 little burn spots across the face of this thing, and 500 little burn spots over here too, probably. And eventually you get enough little burn spots that when you suck that together, it just doesn't make contact, and you don't get any flow of electricity from here across to here. And that's when we say, well, the solenoid's failed, and we replace the solenoid. Some starters, that's actually built into the starter housing. Many of them, it's external. So I would say that is actually the most common failure we see in this whole electric starter motor circuit. So if we ask the question, does the engine crank over or not, and we hear the answer is yes, it cranks over fine, it just doesn't start. Is the battery the problem? Because if the battery was the problem, it wouldn't spin it over, right? Does that make sense? You would be surprised how frequently, though, we get folks that'll call us up and say, well, you know, it spins over fine, but it didn't start. And so I hitched a ride to town and got a new battery and put in it, and it didn't make any difference. Well, of course it didn't make any difference, because if the battery was the problem, it wouldn't spin the motor. Oh, it wouldn't spin the electric motor to crank. Any questions about that before we move on? Mm-hmm. There was some philosophy there that by doing that, there was a little bit less arcing involved when you opened contacts. It proved not to be totally true, and it was enough of a confusion that they kind of did away with that in the 50s for the most part. But all they did was the circuit I just drew, they just designed those motors to work with the battery put in it backwards. And the actual science of it says that the terminal that's labeled negative, that's actually where the flow of electrons is coming out, and it's actually they're actually coming back into the battery on the positive terminal. Because there again, if you remember from your science class, why we've got atoms, and they have the nucleus, and then they have the electrons that are flying around. Those electrons are negatively charged, and we're taking those negatively charged electrons and forcing them around as in our electrical systems. So the flow of those actually is coming out of the battery on the negative post and returning into it on the positive post. And there were some thoughts that it would work better if we broke the circuit on that negative side. And in some cases it does. But for quite some time, as you're aware, why most everybody's standardized where we're taking the negative post and connecting it to our commons, and we're switching on the positive side. When you're jump starting from one vehicle to another or from one battery to the other, you know, I can't say I've done enough of that to be a real authority on it, but my thoughts, Wayne, would be The negative side of the battery is still the negative side of the battery no matter where we're switching. And so I really think you'd want to negative to negative and positive to positive, irregardless of how we're switching the circuits in this vehicle versus how we're switching them in that vehicle. And the vast majority of those that were negative ground were also 6 volt. Or excuse me, that were positive ground. I said it wrong, but yeah, those. I guess I had a tractor that was a 6 volt positive ground, and put a different voltage regulator on the generator and shoved a 12 volt battery in it and used it that way for years. And it worked okay. That was when old Chuck was still at C&C Auto Electric, and they were still on West A, and told him what I had in mind, and he said, "Oh, sure," and he grabs a voltage regulator off the shelf and says, "Put that on your generator and you'll be fine," and he was right. Yeah, I do too. And for those of you that may not know, there was a fellow named Chuck that worked at a business called C&C Auto Electric here in Torrington, and they specialized in rebuilding starter motors and alternators, and did a really good job of it. Chuck's about 3 days older than dirt now, and he's mostly retired, and the business has changed hands. And even before Chuck retired, he was struggling there at the end with getting good quality parts to work with. A lot of the suppliers that he had used for years had gone out of business, and some of the others had moved their manufacturing overseas. And so unfortunately, I think that's a tough business to be in these days, for the fact that it seems to be really tough to get good quality parts to work with. Unfortunately, yeah. And you can't find any of those that are built here either. And I guess on a related subject, I'll just comment that our shop policy is we do not rebuild, or excuse me, we will not install exchange rebuilt starters and alternators because the failure rate on them is so incredibly high. You know, what I'm talking about is the ones you go to the parts store and they'll hand you a rebuilt alternator and they'll take yours in exchange. At one time, that was a feasible plan, but for quite a few years now, the failure rate of those exchange rebuilds at all the parts stores, and I ain't picking on any one parts store, but the failure rate of those has been so high that we just won't do it anymore. So if we ask the question that the vehicle's not starting and it's spinning fine, then we're looking at an actual problem with the engine. And I guess with our engine, like we've talked about, combustion is what we're needing to make happen. And combustion is fire. So I wanted to talk a little bit. If you go to a fireman's convention, they'll talk about the triangle of fire. That to support fire, you have to have 3 things. You have to have fuel, you have to have oxygen, and you have to have an ignition source, a spark, a heat source, something like that. If you take away any one of those 3, the deal collapses, right? So you can have fuel and spark. You can have a big pile of firewood and all the oxygen in the world. If you don't strike a match, there's no fire, right? And likewise, you can take away any one of the 3. In many cases, in modern firefighting, what's done is we try and take away the oxygen. Well, you can have fuel and you can have all the sparks in the world, but if there's no oxygen, you're not going to have any fire, right? Well, I was taught to think about no start crank but no start conditions in an engine in a little bit of a similar way, except our instructors said, well, in an engine, we got to add one more thing. So we're going to talk about a box here. So we're going to have fuel and oxygen, and we have to have a source of ignition. But there again, if we have just those three, it's not a very impressive combustion. You get a little woof and okay, wow, that was cool, but we don't get the forceful kind of combustion we need to push that piston down if we haven't compressed it all. Taking this atmospheric air that's 20% oxygen and condensing it into an oxygen-rich environment that's all tightly compressed really makes that explosion much more violent and therefore much more powerful to push our piston down. And honestly, you can have all three of those things on top of that piston, but if it hasn't been compressed, that combustion isn't forceful enough to push that piston back down the bore. So our fourth side that we typically look about is compression. So if we have one not wanting to start, we start thinking about which one of these we might be missing. This is not 100% true, but in general, if you've been used to using this engine, you kind of know what it sounds like when you crank it. And if you're cranking it and it sounds a little funny and it sounds like instead of the normal rhythmic, you can kind of hear the compression. As one goes, rrr, 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 that's the compression interrupting the speed of the electric starter motor. And if you don't have compression, there's no resistance against that electric motor, and it typically will spin it real fast. Instead of 150 RPMs, one of these with no compression might spin 400 RPMs pretty easily, actually. So a lot of times, something I do is just listen and see if that sounds kind of normal. If it sounds like it's spinning real fast and real free, and I'm not hearing those compression interruptions to the normal rotation, I might go looking for that. On the oxygen side, for the most part, if our duct that brings air into our engine isn't plugged up, we probably aren't going to have an oxygen problem. But you'd be surprised how many vehicles have been towed into my shop that I open up the air filter box to just look and see, and it's packed full of cheatgrass and dog food because the mice have carried it in there, and it's so plugged that the engine can't get any air to work with. So it's pretty quick and easy to just open up the air filter box and take a quick look, see if there's any restrictions there keeping us from getting air. Depending on how sophisticated the electronics and whatnot and some of the preheating systems are in the engine, but a lot of times on a lot of engines, you can take a can of starting fluid and sniff a little bit of it at the engine, and if it kind of tries to start on the starting fluid and it didn't before, well, that tells you were missing the fuel side of this equation. Now, of course, gasoline engines, our source of ignition is going to be our spark plug. On our diesel engines, it actually is the compression combined with when we're injecting the fuel into it. But a lot of times, let's talk about a gasoline engine. If we've listened for the compression, we've opened up and made sure there's no restrictions in the flow of air, we've given it a little sniff of starting fluid, and that didn't make any difference, then we might want to look, see if we've got any spark. And a way that's typically done, so this is our spark plug wire that's normally going to take our spark to our spark plug. If we pop that off, and by the way, I would not recommend cranking an engine with this just laying around. Most things we have these days have computers, and if that spark doesn't have a good way to go, sometimes it finds a way up a wrong wire and can fry a computer real easily. So before you hit the key and start cranking one, you want to have somewhere for that spark to go. And what we do a lot of times, we'll just take a spark plug off our toolbox or whatever, jam it in there, and lay it against part of the main metal of the engine. So we're grounding the shell of the spark plug. So this is configured like it would be if it was inside the engine. The only difference is it's out where we can see it. And if you can be where you can see this and crank it, or in some cases you need a helper to crank it, and you're going to look, see if you're seeing a spark jumping across that gap. That's what you're looking for. Now you want to kind of be a little careful because you can zap yourself. But there again, don't feel like you're going to die or nothing. It's not enough electricity to cause any serious harm, but it does smart. Because there again, if we think back to our analogy of amperage versus voltage and our kitchen sink, it's like one drip of water coming out of that kitchen faucet, but it's coming out of there at 100 miles an hour. So if it hits your hand, it kind of smarts, but it ain't enough you're going to drown in it. Does that kind of make sense? So that's a common way to check for spark. And if you go through that you can typically go through what we just talked about in a matter of 10 minutes and have a pretty good idea why this engine isn't starting. So that's the way it was talked about a lot. We'll say 25 to 30 years ago. But not long after that, some guys came up with an acronym that I actually really like. And it adds a couple of more possibilities to that, which are valid, very much so. Although I'm just going to write it up here. So the acronym is FASTECH. Now, you're probably aware of the fact that us guys who used to be called mechanics, why everybody likes to call themselves technicians now. And this came out as an idea that if you want to be a fast technician, you can use this idea. And it really works well. So the idea is check for fuel first. And there again, there's two sides of that fuel in most modern engines. You got to get the fuel moved from the tank up to the engine. And then you've got to have your injectors taking it and putting it in the cylinders. And at times you need to look at both sides of that. And depending on the configuration of the engine, sometimes the shooting a little starting fluid at it works well, and sometimes not. But if that is something you can actually get the ducting apart and do, it's a pretty good way to tell if you're getting fuel in the cylinders or not. And if you're not, then you back up and look and say, hey, is it a problem with the injector squirting it in? Or is it a problem getting in from the tank up to the injectors? And you break the whole thing down in pieces, and the pieces of the puzzle are pretty manageable. Then you look, for your airflow. And there again, that's usually just as simple as making sure there's nothing restricting the flow of air. The other thing that in modern engines can cause an affliction here, what if that air that is going into our engine, and this usually applies more to engines that will cough and sputter and try, but won't really quite run. This won't be the case if they just do nothing, as far as don't have any try to them. But like we talked about, the exhaust gas recirculation, because what we're wanting out of the air is oxygen, right? Well, if that exhaust gas recirculation system is stuck wide open, it's taking all the exhaust, which is inert gas, and recirculating it back in. And that's only supposed to happen at certain times when you don't need full oxygen and full power. But if it's malfunctioning and you're getting all that inert gas shoved back in, you don't have enough oxygen to work with. So as far as the air goes, like I said, something to keep in mind is one that tries, but it's just awful puny and won't quite go. That is a possibility. So S is for spark. And so if we do like we talked about there and look, do we have spark jump in our spark plug? And if not, then we back up and see why. And there's several steps to that, including, like we talked about a minute ago, if our transponder key isn't communicating with our theft prevention system, it won't let that spark on a lot of vehicles, because there's getting to be more and more vehicles that instead of that theft prevention interrupting the starter circuit, it interrupts the circuit that makes the spark. So you can have a wrong key and jam it in, and it'll actually spin the starter, but it won't let the spark go to the spark plug to actually make the engine run. So that's kind of a side note to keep in mind on that. But then T is for timing, because as we've talked about, all the cycles of our 4-cycle or 4-stroke engine, that stuff's all got to happen at the right time. And there's 2 timing things to think about. One of them being spark timing. Is that spark we're seeing happening at the right time? Is it happening right there between our compression and our power stroke? Or is it, for some reason, getting that spark out in the middle of our exhaust stroke? The other timing is what in many cases are referred to our mechanical timing, or a lot of us call it our valve timing, as far as the timing of when our intake and exhaust valves are opening and closing in relation to our piston travel. So there's, as far as the timing goes, thinking about spark timing, or if it's a diesel, well, that would be our injector pulse. Because there again, okay, if the sensors are whacked out and it's firing the injector over in at the beginning of the exhaust stroke instead of at the right time, well, that's obviously not going to work. What do you think E's for, Joe? Any ideas? I'll give you a hint. It's one of our 4 strokes. Okay. There we go. Good job. So this is not real common, but it does happen. If we've got plugged flow of the exhaust, we can't take out the trash builds up and we can't build a new fire. Same as, okay, in your fireplace, if you pack the whole thing full of ash, you can't get a fire built in there. Well, if we can't get all the inert waste gas out of our cylinder, we can't bring in more oxygen and fuel. So couple of things that we do see there is exhaust pipes that get smashed shut. You're driving, it's easy enough to run over something and smash that pipe shut. But what we see far more often than that is if typically the exhaust after treatment emissions devices, catalytic converters and diesel particulate filters, if they're plugged up, they don't let the exhaust out. That can also happen in the muffler. And when we had carburetors, we saw a lot more of that because there again, the carburetors created a lot more carbon and waste particulate that would plug up the muffler. In modern vehicles that have a lot better air fuel mixtures and create less of that trash, boy, we just don't see plugged up mufflers, hardly any. The only one I can think of having in our shop in the last 5 years was actually a vehicle that had set over the whole winter and the mice had packed it full. And so it was actually a mouse nest plugging it, not plugged full of waste from the engine. So C is for another one of our 4 strokes. Yeah, yeah. So typically, if we've got a lack of compression, we've got a fairly major problem with our engine. It can be related back to timing, because there again, if our valves are not opening and closing at the correct times, we won't have any compression. For example, if when our piston's traveling up to do our compression stroke, our exhaust valve is open, well, we're not going to compress anything. We're just pushing it down the tailpipe, right? But the more common causes of a lack of compression, we're going to draw our cylinder here again. And we've got our intake valve and our exhaust valve and our piston here. So to have compression, we need all that sealed, and then we shove the piston up and compress it, right? So any place that we let air out of that will be a problem in this whole process. So if we've got a problem with this valve, that there's a burned edge of it and it can't close there, well, when that, and this is our intake side, when that piston comes up, all our air that we put in there, we're just going to push it back up the intake manifold, right? Likewise, if that happened on our exhaust valve, and we've got a chip out of this valve, or we've got a crack missing out of the valve seat, well, when that piston comes up, all our air, instead of compressing, goes out the tailpipe. So our piston rings that seal the sides of this piston to the cylinder walls, if we've got a broken one of those, or we've got a big gouge here in the side of the cylinder wall where that ring can't seal to, all that air that we wanted to keep in here can go down past our piston into our crankcase. So those are common issues for lack of compression. And something that I've done quite a bit, because here in the top, you're going to have some kind of an opening. If it's a gas engine, you'll have a place for the spark plug, and we can screw the spark plug out. If it's a diesel engine, you're going to have an injector. You may have a glow plug too, depending on the design. But what we do a lot of times, if we've got a cylinder that we suspect has a compression leakage problem, we'll do one of two things. But we will take one of the mechanical devices out here so we can screw a test fitting in. And in many cases, that test fitting is a gauge. And it'll have a dial on it, and we can crank the engine over, and typically these compression test devices will have a check valve in here. And we remember what a check valve does, Chase? Good job. So when that piston comes up, it'll let that compression go into our test gauge, but when the piston comes back down, it doesn't let it out. Can you think why that would be useful? Right, because if we're cranking this at 150 RPMs, our gauge would be doing this 150 times a minute, and it's kind of hard to see where that needle stops, right? So we want to see where it stops. In relation to that, modern gasoline engines typically are going to, a good one's going to run somewhere in that 135 to 150 psi. That's pounds per square inch. There again at 150 RPMs. Because we always have some leakage past our rings, they're not a perfect seal. There's that gap in the end and whatnot. This pressure will be noticeably different if the speed of the cranking is noticeably different. So there's no point in trying to run that test if you've got, bad battery cables and you can only crank it at 50 RPM. Did you have a question, Joe? So say that again. I didn't quite catch it. Right. So if instead of this being out into the cylinder wall like that, there was a ridge sticking in here like this, is that what you mean? And that does occasionally happen. And what normally will happen is as this piston ring, so let's grab a piston with a ring on it. So this ring here, if there's a ridge sticking out like that, as that ring comes up and hits that, it'll break that ring, is what we typically see happen. And as you can imagine, well, if that ring breaks, and then there's a broken piece of ring between the side of this piston and the cylinder wall, it just chews the snot out of them both. Right, exactly. And one of the reasons that happens, so you'll notice that most our pistons are aluminum. And our cylinder walls are typically cast iron because this ring running up and down against cast iron, they found alloys of iron and alloys of the steel that these rings are made out of that they can make work together and last pretty well. Aluminum's actually a pretty soft metal. They've experimented with aluminum cylinders. Nobody's ever made it last. There are some short life engines that will have aluminum cylinders with a nickelized plating in them. And, some of the chainsaws and stuff will have that, but there again, they don't last. 100 hours on one of them engines would be long life if you're really lucky. So anyways, we got a cast iron cylinder and we got aluminum piston. And we've designed this thing, well, I shouldn't say we, but the engineers designed this thing so that at 200 degrees, when this piston's running about 200 degrees and this cylinder wall is about 200 degrees, there's still enough room between the two of them for a little bit of oil film and room for this to go up and down. Now, the oil film thickness, typically we're talking like 2 to 4 thousandths of an inch. Well, if instead of running at 200 degrees, we hit, we'll say 300 degrees, what happens to most everything is it heats up. Exactly, that's right. So does everything expand at the same speed? So if we heat this up 100 degrees and we heat this desk up 100 degrees, are they both going to grow the same amount? Because they're made out of different materials, right? This is not exactly true, but it's pretty close. Aluminum, as it heats, expands twice as fast as iron. So if instead of running at the 200 degrees we designed this to, we're at 300 degrees, that cast iron cylinder may have expanded 10 thousandths of an inch. That piston may have expanded 20 thousandths of an inch. There's not room for it in there anymore. And so we're dragging the sides of it like crazy, and we make it look like that. And the aluminum will actually peel off of here and ball up, and then those balls will gouge the end of the iron. And, well, we wind up wrecking them both really bad. The piston, will, because the aluminum is softer, will go south faster, but we'll wreck them both. But that's typically what happens is the piston expands to where it's bigger than the cylinder, and there's no room for the oil, and so it squeezes all the oil out, and it's metal to metal with no lubrication and crashes it. Because of course this used to look like that. So anyways, back to our diagnosis here on our diesel engines, the numbers, because there again we're igniting our fuel with the compression. I think I need to, on our diesel engines, an ideal engine will run 375 to 400 psi at that same 150 RPM. Interestingly enough, at that RPM, well, yeah, at that RPM, you typically won't have one start if it's under 300. And usually if one's down 325 or so, the reason it's down is there's enough leakage here at the rings that, you know, during some of the strokes, we're pushing combustion gases this way past the rings, but during other strokes, we'll be sucking oil past the rings, and it'll actually be an engine that uses oil. One that's at 300, if you have an engine that only one cylinder's at 300, or even 275, that engine will idle on the other. Well, for example, if it was this 6-cylinder, it'll idle on 5 cylinders. And you can tell it runs uneven. And that one cylinder that's not firing, we call a miss, because it's misfiring on that one cylinder. So it'll have 5 even combustions, and then a gap where you can tell one should have fired, but it didn't, and then it'll hit on 5 again. But typically, you know, down at say 275 at idle RPM, which is 700 or 800 RPMs, that engine, or excuse me, that cylinder, if you got one down at 275, won't create enough heat and pressure to ignite the diesel fuel, and it'll miss. Once you bring the RPMs up to say 1500 RPMs, at that speed, the piston's coming up enough faster, it'll fire on that cylinder once you get. So pretty often if we see one that's missing at idle, but you bring the RPM up to 1500 RPMs and the miss goes away, a lot of times we know that it's got one cylinder that has low compression. It's not got no compression, but it's got low. Yeah, Conan? Correct. Right. And you're right on track, because that was kind of the next thing I was going to talk about is, so like I said, one of two things we will do here. Either that one where we put a gauge here, or in some cases we'll instead put a fitting in there we can hook shop air to. And when we put the shop air to it, what we will do is and you can do this sometimes with the ones that are running on part of the cylinders as well. But what we will do is, okay, that air is escaping, but we want to know where. Well, if that air is escaping here past the rings, it's going into the crankcase, and the crankcase is all everything that's in housed inside the engine. So something we do a lot is take the oil fill cap off, because that's a big opening in that crankcase. And if you hear a lot of the air coming through there, well, you know it's coming between the piston and the cylinder wall. So, Cole, what do you think would be the issue if we put compressed air in the top of the cylinder and we hear it back at the tailpipe? Exactly. The exhaust valve is open. Now, either the exhaust valve is damaged or there's problems with the system that opens it being out of time, and but we know that's the source of the loss of our compression. It's going out the exhaust valve. So, Joe, what if we hook our shop air up here, and that hose where we had our air filter, we hear all the air rushing out there? I'm sorry. The air rushing. So we've put compressed air from our air compressor, our shop air compressor. We've put it in here at this point, and we hear that air rushing out the tube that normally goes to our air filter, the tube where we normally have our air going into the engine. What would be a likely fault? Exactly. Exactly. Good job. So if the intake valve is the fault, so if you've got a lack of compression, those are some things to kind of figure out a little bit what's going on before you spend all the time it takes to gut that engine and tear it all down in a million pieces. Um, and it's usually really helpful to kind of figure a lot of that out. If every time we had one that didn't start and run, we just totally disassembled it, labor bill would be pretty high. Right. That's exactly right. Right. If we're midway through the exhaust stroke, well, that valve should be open. And that's a very good point, in that when we're doing that test where we put compressed air in, um, we ideally want to have this piston at the top of its stroke between the compression and the power stroke, because that's where we want the highest compression, is right there at the point where we would normally be igniting it. Now, the thing you got to watch out for a little bit is if you haven't figured right and you don't have that to just the right spot. Let me grab this and maybe make an example. So, of course, with the engine assembled, we can't see the piston, but what we're wanting to do is test it when it's right there at top, and it's, so that one right there is between the compression and the power stroke. But if we didn't figure that out right from markings on the external part of the engine and whatnot, and we have that right there, what's going to happen when we put our shop compressed air through the spark plug hole? Well, it will do all of the above, but the thing that can rip your knuckles off is if that shop compressed air does this, and your knuckles were in the way over here. Because if that if there's not a massive leak of compression, it's just, we're losing part of it. It's pretty common that if you don't have that right at the top and you're off whack a little bit, when you put the shop air to it, it's going to spin that crankshaft pretty violently and suddenly. So you kind of want to do your best to have it in the right place, and you want to have all your body parts out of harm's way in case you're wrong. Well, you could try that too. And usually that'll work if you're braced the right direction. But if you're thinking it might go that way and instead it goes the other way, it can still bite you. So there's a fella that has a pretty neat video about what we just been talking about, and I thought it might be fun to watch this. I think it's like a 13-minute video, and I guess that'll run us just barely over. Is that going to put anybody in a bind? Shoot, I pushed the wrong button. Let's try again. Well, that's a good sign, Joe. That means maybe it's warming up. Can we catch? I think I hear it kicking in. Can somebody catch part of those light switches for us, please? Well, where's our audio? What, Cole? Can you see it okay? All right. Hmm. Well, it's still playing on the actual computer. It's just a problem with the projector, it appears. So let's, okay, see if we can get the projector going, and I'll set the video back. Well, the little green blinky gives us hope, but is it going to do it? Hmm. Well, it's not very bright, but we'll give it a try, huh? So, if you didn't recognize it, what we've been talking about as intake stroke, compression stroke, power stroke, and exhaust. This is a real common way it's described around a lot of shops. Um, Suck, squeeze, bang, blow, and sometimes this is referred to as smash, suck, smash, bang, blow. But that's talking about the four strokes. We've been talking about the whole class. So just a fun way to say it. Now, if you would, I'm going to back this up just a little bit and listen to that when he cranks it. You can hear one compression, and then you hear the starter run free, and then you hear one, and then you hear it run free, and you hear it run one. So listen for that if you would. So we'll give you a little hint. That would be the right sound for a single cylinder engine. This engine has two cylinders. So, like he says in his caption, after spraying that little bit, well, it would do something if fuel was the missing element. And he kind of fast tracked past the air one. When he pulled that air filter and stuff out, well, he could see right in the bore of the intake, and there wasn't anything restricting the airflow. So when you're seeing melted junk all over an engine, what's that a sign of? It got hot. So he's taking a spark plug out. So that guy's kind of fun, but I thought that was a good little snapshot of a good way to approach figuring out what's wrong with an engine. Well, he figured out that it's got mechanical troubles inside the cylinders and needs tore apart. Um, but like he said, in many cases, you'll wind up finding out you're missing the fuel element or you're missing the source of ignition, which there again on a gas engine's your spark for your spark plug, or in our diesel engines, it's you're missing that fuel pulse that starts your flame travel. Um, but that's a good approach to sorting out problems. Um, Anybody got anything to add to that? Well, thanks everybody for coming tonight. I did not do a quiz for tonight. Um, oh, there you go, Conan. Um, and I guess we had kind of made the plan. We'll